All right, hello. Here's our video for section 5.3, which is all about the sum and difference identities for cosine. But before we get into that, I want to quickly just make sure that we all remember the identities that we've learned over the last couple of videos. So I'm going to have you pause the video, and on this first page of section 5.3, go ahead and take a moment to fill out all the identities we've gone over. If you can't remember, just let the video play and I'll fill them all out. But go ahead and pause it, do your best to fill these out, and then when you're ready, play the video again and we'll go over them, okay? Okay, let's see how you did. So on the first little section here, we're talking about reciprocal identities, which hopefully you guys are able to just crack out like no problem. We know that cotangent and tangent are reciprocal identities. We know that secant and cosine are reciprocal identities, and that cosecant and sine are reciprocal identities. So hopefully you were able to fill all of those out. Then we have our Pythagorean identities, which we used extensively in section 5.2, right? And so our little reminders for that is you sin, you confess, you're one with God, right? Sine squared plus cosine squared equals 1. And then 1 tan second, only takes 1 tan second, right? So 1 plus tangent squared theta equals secant squared theta, and then our last one was 1 cocos, right? 1 plus cotangent squared theta equals cosecant squared theta. So hopefully these are becoming a little bit more familiar to you now that we've done some homework involving their use. And then we also had our negative and our quotient identities. So negative identities, these are going to come into play a lot with the identities that we're learning. So when it comes to negative identities, if you see sine of a negative angle, cosine of a negative angle, tangent of a negative angle, we're looking for what can we replace that with. And the only one that doesn't change the sign, the plus or minus value, is cosine. So cosine of a negative angle is the same thing as cosine of that positive angle, okay? But sine and tangent, the value actually changes sign, meaning from positive to negative. When we go from a negative angle to a positive angle, we get a negative sign value. We go from a negative to a positive angle for tangent, we also get a negative. So that is also true of their reciprocals. Notice secant does not change values, but cosecant and cotangent do change values. Okay, so make sure you're familiar with those negative identities. And then tangent and cotangent we went over, that they can be written just as a ratio of our sine and cosine values. Tangent is sine over cosine, which means that cotangent would then be cosine over sine. Okay, so again, make sure you're really familiar with these identities so that on an exam you're not spending a whole bunch of time trying to figure out the identities. If they're really nice and fresh on your mind, then you'll be able to recall them easily when you're working through homeworks and exams. Okay. All right, now this next page I am actually not going to go over. This is just kind of recalling where the distance formula comes from. And the only reason we would need to know where the distance formula comes from, this is doing an example with the distance formula, is this is what you actually use to prove the identity on the next page. But I'm not going to go through the proof, so I'm not going to waste video time going and recalling the distance formula. But I just wanted to mention that versus just skipping over the page and not saying anything about it. So, you know, it's not something that I would put on a homework assignment or an exam, okay? So this is a really complicated looking hot mess, right? Basically, we're trying to prove this identity right here. That if we are given two angles, A and B, or you can think of this as your first angle and B as your second angle. A lot of times when I work through these problems, I'll refer to it as this first angle and the second angle. But for our formula, we're just going to use an A and a B. So what we're trying to do is derive this identity. And I'm not going to go through the whole process because really you don't have to understand how it was derived to make use of it. So I'm not going to spend a bunch of time on that. If we wanted to prove it, if you were if you are interested in how to prove this. Basically, all we would have to do is set these dotted line distances equal to each other, and then do some algebra to come up with this true statement. Again, I'm not going to go through that because I'm much more concerned about you actually using this identity versus deriving it. So I'm going to go ahead and just scoot up here. So why do we care? This looks really complicated. So our big question is, in regards to this formula, why bother, right? What's the point in knowing this formula? So why we care is we really want to be able to get exact values for our trig functions, right? Exact values. And not all angles come out with pretty values. Some of them, I mean, we can get like a rounded decimal for it, but only those like really nice like quadrantal angles come out with like really nice values, right? They can be computed precisely. Same thing with our reference angles, right? Our nice like 30-degree angles, our nice 45-degree angles, our nice 60-degree angles. All of those we can come up with an exact value that's not too bad to look at, right? Because we have those reference triangles, so we can find exact values for them. But there are some that don't come out pretty, right? Like if I ask you to find cosine of 15 degrees, right? 15 degrees, we don't have a nice pretty reference triangle for it where we can calculate, you know, the adjacent over the hypotenuse. So why we bother is because identities like this allow us to precisely calculate the trig values for more angles. Okay, other than just our nice quadrantal angles and our nice angles that have pretty reference triangles. Okay, so basically what we want to do is we want to be able, if we want to find cosine of some ugly angle, right, that's not one of our quadrantal angles and not one of our nice reference triangle angles, what we can do is try to write that value, whatever angle we're dealing with, if we can write it as a difference of two of our nice pretty angles, then we can actually calculate it. So, or in other words, what we're hoping to do is we want to write whatever our angle is. So I threw out cosine of 15 degrees. 15 degrees does not have a nice reference triangle. So if I'm saying A minus B, this angle that we're trying to find the cosine value of, if I can write that value as a difference means we're subtracting, as a difference of angles with nice values, right? Our nice pretty reference triangle angles that we can compute. We can compute. Okay, so let me just show you what I'm talking about here. So for example, if I want to find cosine of 15 degrees, what this formula says is if I can write this value inside my parentheses, so in this case 15 degrees, if I can write that as two nice pretty angles being subtracted, then I can calculate it using the sine and cosine values of those nice pretty angles. So what I'm thinking is I want to try to write this as the cosine of some nice pretty angle minus some other nice pretty angle, right? So do I know two nice pretty angles that when I subtract them, it gives me 15 degrees? And I do, right? I could use 60 degrees and 45 degrees, right? Because 60 has nice pretty trig function angles because we have a reference triangle for it. Same thing with 45, and 60 minus 45 is 15. We could also do it with 45 and 30, right? 45 degrees minus 30 gives us 15 degrees. So there are different ways to calculate this, okay? So when you're working through your homework, keep that in mind. All right, so now that I've been able to write this as a difference of nice pretty angles, right? What I'm going to do is I'm going to think of this as my first angle and this as my second angle. And I'm just going to plug it into this new identity that we have. This new identity says that once we know what our first and second angles are, then this is the same as doing cosine of the first angle. So that means cosine of 60 degrees times cosine of the second angle. So cosine 45 degrees, right? Plus sine, actually I'm going to run out of room here. Let me write it down here. So this is going to be cosine 60 degrees, cosine 45 degrees. I'm just rewriting it down here. Sorry about that. Plus sine of our first angle. So our first angle is 60 degrees. And then sine of our second angle. And our second angle is 45 degrees. Okay. So even though I rewrote this nice little cosine of 15 as this big mess of nastiness, this is now something I should be able to get an exact answer for, right? Because I can easily use reference triangles to find what cosine of 60 is, what cosine of 45 is, what sine of 60 is, and sine of 45. Now, to make your homework experience a little bit smoother, if you look on page 4, I actually included a trig functions chart and a unit circle. So both of these will give you the same values. It's just whatever format you like best. So if I look at this chart, basically I look up in degrees. Like, so if, like on our first one, we need to know what cosine of 60 degrees is, right? So on this chart, I would go to my degrees column and go down to 60 degrees and then go over until I find that cosine value of 60 degrees. Okay, so we can see here that it would be 1/2 is cosine of 60 degrees. Okay, so that's how you use the chart, or you can use the unit circle. So for the unit circle, I would just go up to 60 degrees, which is here, and then we know that cosine of 60 degrees is the first coordinate of that ordered pair, which again is 1/2. So both of these are going to give you the same information. It's just dependent on, you know, do you like the chart or do you like the unit circle? I kind of prefer the unit circle, so that's probably what I'm going to reference in this video. If you like the chart better, that's totally fine. Okay? All right, so let's go ahead and fill in our values here. I need to know what cosine of 60 degrees is, which we just found to be 1/2. Then I need to find cosine of 45 degrees. So on the unit circle, I'm going to go to 45 degrees, which is right here. And I'm looking for the cosine value, which is the first value in the ordered pair. So that's square root of 2 over 2. So cosine of 45 is square root of 2 over 2. Plus, I need to know the sine of 60 and the sine of 45. So I'm going to flip back over. I'm going to go to 60. And I'm going to take the sine value, which is the second value in the ordered pair. So that's square root of 3 over 2. So sine of 60 is square root of 3 over 2. And now I need to figure out what the sine of 45 is. Okay, so again, flip over, go to 45, which is here. The sine value is the second value in the ordered pair. So sine of 45 is going to be square root of 2 over 2. So I'm going to flip back over, square root of 2 over 2. And now that I know those values, now I just need to simplify this, right? Because the idea is I want an exact answer, not a decimal representation. So when I multiply fractions, I multiply straight across. So this gives me the square root of 2 over 4 plus the square root of 6 over 4. And then because we want one nice value, we are going to go ahead and write this as one fraction. So since they have the same denominators, we can add the tops. And remember, with radicals, we can only combine the radicals if they're the same root and they have the same thing under the root, which in this case, these are not both square roots of 2. They are not both square roots of 6. So we can't actually combine them, but we can add them, write them as an addition statement in the numerator. So this would be the square root of 2 plus the square root of 6 all over 4. And we just leave it like that. Okay. So this is going to be hugely helpful for us, hugely helpful if that's a way of saying things, because now we're able to take something like cosine of 15, which normally if we were to calculate this, our calculator gives a decimal approximation, not an exact answer. Okay, so I'm not saying we weren't able to calculate cosine of 15 before. We were actually able to calculate cosine of 15, but it gave us a decimal approximation of that number, not an exact answer. So using this difference identity for cosine, we can actually get an exact answer for a trig function that otherwise all we could get was a decimal approximation. Okay, so this is why we care. That's where we're headed. So what I want to do now is I want to give you the other identity for cosine. So this one was using the difference identity, right? And we actually also have an addition identity for cosine function. So I'm going to go ahead and move this page over. If we look at the top of page 5, now we have two identities. What we want to do is we want to take this first identity that we just came across on the other page, right? This is the one we just used. And we're going to derive this second identity, which is the addition one. So now we have two identities. So these are two identities we want to be super duper familiar with. I'm just going to go ahead and say these are ones that you must know. And they're not too hard to remember if you think about it, because we're only talking about cosine. And notice on both of them, they start with cosine of the first angle times cosine of the second angle. And then in the second term, it's just sine of the first angle, sine of the second angle. So the only difference in these two identities is that if we start with a subtraction, we add the two terms, right? And here, if we start with an addition, we end up subtracting the two terms. So I want to go ahead and prove this. And this is something you should be able to do, is to start with one and prove the other one from it. Okay, so I'm going to start with the left-hand side, and I'm going to start with the second identity. That's the one I'm trying to prove, right? Which is that cosine of A plus B is equal to, and I want to end up with this statement, right? So what I'm going to do is I want to be able to write this as a difference, because we already know the difference identity, right? So if I could write this as a difference, then I could just plug it into this first identity. So how would I be able to write what's in here as a difference, right? As a difference, okay? Well, if I have A plus B, a positive, we can get by combining two negatives, right? So I could rewrite this as cosine of A minus a negative B. Do you agree with me? Because anytime we have double negatives, that becomes a positive. So it's kind of like using that rule, but backwards. So I'm just going to rewrite this as A minus a negative B, because I have not changed the value in any way. I've just rewritten it in a different way, right? So now what I can do is I can consider A to be my first angle, and I can consider negative B to be my second angle. So I'm going to plug in A and negative B into my difference identity, okay? So my difference identity says that we do cosine of the first angle times cosine of the second angle. So that's going to give me cosine of A times cosine, oops, I wrote sine. I said cosine and I wrote sine. Silly me. All right, so we have cosine of the first angle and cosine of the second angle. And the cosine of our second angle is negative B, right? Plus, now it says to do sine of the first angle times sine of the second angle. So sine of the first angle A, sine of my second angle, which is negative B. Now, we're trying to prove that this cosine of A plus B is going to end up with that. Now notice, if we look at that, we're ending up with only positive A's and B's, not negatives. So I'm going to go back to those negative identities that we did at the very beginning of the section, right? All these identities we have to remember. If I look at the negative identities, anytime I have a negative angle, I can rewrite it as the positive form of that angle. If it's a sine, it just becomes a negative sine value, and I can write it with a positive angle, right? If it's a cosine of a negative angle, I can write that as just cosine of the positive angle. So let's see how we can apply those in what we have here. So notice this one right here, I can rewrite using the negative identity. And this one right here, I can rewrite using the negative identity, right? So I'm going to go ahead and rewrite this. So the first one is cosine A. Now cosine of a negative angle, remember our negative identity, cosine of a negative is the same thing as cosine of the positive angle. Nothing changes, right? So I can just rewrite this as cosine B, because cosine of negative angle is the same thing as cosine of the angle. Okay? Plus, over here I have sine A times, now sine of a negative angle, remember if we look back at our identities, when we have sine of a negative angle, that we can still change it to sine of the positive angle, but it's going to change the value to a negative, right? So sine of a negative angle is equal to the negative sine value of that positive angle. So on this one, if I want to rewrite sine of negative angle B, that's going to be the same thing as negative sine of a positive B. Okay? So now you can see that on this term, I have a positive and a negative. So when I multiply those together, that's going to give me a negative product, right? So this gives me cosine A, cosine B, minus sine A, sine B. So in other words, when I multiply these two together, it's going to give me a negative product, right? And you can see now that this is exactly what we were trying to prove. This is the right-hand side. Right side. So we have proved it. Okay? So this is something that you should be able to do. Okay, I'm going to write over here, should be able to prove. Okay, this is something that I may or may not put on a test for you to take a given identity and be able to derive the other one. Okay. All right. So let's look at how we're going to use this new identity. Same idea. We can use these cosine sum and difference identities to calculate trig function values for angles that otherwise all we would be able to do is have a decimal approximation, right? So let's look at the first example. We have cosine of negative 75. Okay, and we want to find the exact values. That means no decimals. Okay, that means we're going to have something like we did on the other page. Something like, where is my other page? Something like this. This is an exact value because it hasn't been rounded. It doesn't have repeating or ongoing decimals. It is the exact value. Okay, so that's what we want to do for these. So I'm going to go ahead and use our addition identity just because that's our new one. So let's get some practice with it. So in other words, what I'm hoping to be able to do is I want to be able to write negative 75 degrees as an addition. So some value plus another value. Okay. So I'm looking at negative 75. If I have to add two numbers and I need to end up with a negative, most likely those two numbers that I'm adding are going to be negative, right? So I need to find a negative angle and another negative angle that have pretty trig function values that when I add them together equal 75, okay? So the only two that I can think of off the top of my head would be 45 and 30. But we need a negative 75, so that means I'm going to use a negative 45 degrees and a negative 30 degrees. Okay, does that make sense? Because then when we add those together, it gives us a negative 75. So that means that negative 45 is my first angle and negative 30 degrees is my second angle. So let's go ahead and plug it into that cosine of a sum identity. So cosine of a sum says that we take cosine of the first angle and multiply it by cosine of the second angle. So for our problem, that means that we're going to take cosine of our first angle, which is negative 45 degrees, times cosine of our second angle, which is negative 30 degrees. Okay. Then our second term says we're going to subtract sine of the first angle times sine of the second angle. So we're going to subtract sine of our first angle, which is negative 45 degrees, and sine of our second angle, which is negative 30 degrees. Now, this is something that I need to look up on one of those charts, either the chart or the unit circle, to find these values. So when you see negative degrees or negative radians, right, you can use the unit circle and just go in the clockwise direction, right, to find those negative angle values, or you can use the negative identities. So I'm going to go ahead and use the negative identities because all those negative identities that we learned allows us to write our trig functions with positive angle values, right, rather than negative angle values. So sine, if sine of a negative is going to turn into a negative sine value, cosine is going to turn into just a positive cosine value. So I'm going to go ahead and use our negative identities here. Use negative identities to rewrite. Okay, so we know that cosine of a negative angle is the same as cosine of that positive angle. So we can write cosine of negative 45 as cosine of just a positive 45, right? Same thing here, cosine of negative 30, cosine values stay positive, so that's the same as cosine of 30 degrees. Then I'm going to subtract my two sine values, right? So sine of a negative angle actually gives us a negative sine value. So this becomes negative sine of positive 45 degrees, okay? And the same thing on this one. Sine of a negative angle gives us a negative sine value of that corresponding positive angle value, okay? And then just to make it a little bit easier on myself, before I plug in the actual values, here I notice that I have a negative times a negative, right? And a negative times a negative is going to give me a positive. So I'm going to go ahead and just eliminate those two negatives by saying, let's think about what this would be if I multiplied those together. It would give me a positive. Now I'm still going to have this subtraction, right? But this negative times this negative would give me a positive product. So I'm going to go ahead and write this as a positive sine 45 degrees, sine 30 degrees. Okay, and we have cosine 45 degrees, cosine 30 degrees, right? All right, and now I'm going to go ahead and plug in my values, and I'm going to bleed over into this problem a little bit, and that's okay. We'll figure it out here in a minute, okay? All right, so cosine of 45 degrees. Again, you can use the chart, or you can use the unit circle. I'm going to use the unit circle. So I go to 45 degrees. I'm looking for the cosine value, so I look at the first coordinate, which is square root of 2 over 2. Square root of 2 over 2. And then I'm looking for cosine of 30 degrees. So again, I'm going to go to my unit circle, find 30 degrees. The cosine value is the first coordinate, so square root of 3 over 2. Square root of 3 over 2 minus the sine of 45 times the sine of 30. So let's find the sine of 45 and the sine of 30. So when I look at 45, the sine value is the second coordinate, so that's going to be square root of 2 over 2. Square root of 2 over 2. And now I need to find sine of 30 degrees. So I go to 30 degrees. I look for my sine value, which is the second coordinate, and that's 1/2. 1/2. Okay. And now that I have it all written out, now I can go ahead and just simplify and write it as one fraction. So square root of 2 times square root of 3 gives me square root of 6 over 4. Minus, when I multiply my other two fractions together, I get square root of 2 over 4. And even though I can't combine the square root of 6 and the square root of 2, I can write it all as one fraction. So this gives me the square root of 6 minus the square root of 2 all over 4. And that's my exact answer for cosine of -75. Okay, does that kind of make sense? So just rewriting the angle in terms of either two angles being added, right? That's the new identity, or two angles being subtracted. And the angles we're choosing are nice, pretty ones, okay? All right, so I want to show you how to use this same method, but with an angle that is in radians. Okay, so when we're given an angle that is in radians, sometimes it's easier to deal with in degrees, right? Easier to work with degrees. So we're going to go back, blast from the past, right? How to change a radian value into a degree value is we take that radian value, 17 pi over 12, and we multiply it by a ratio that will change it to degrees that will cancel out the pi, right? And our ratio is that pi radians is the same as 180 degrees. So we can go ahead and do 180 degrees over pi radians and multiply that out. Okay, that way our pi's will cancel, and if you multiply 17 times 180 and divide it by 12, this is the same as 225 degrees. Okay, so basically what we're trying to find is cosine of 225 degrees, right? Oh, 55. Ah, gosh, 255 degrees. Struggle busing here. 255 degrees. 255. I was going to say 225 is a nice, pretty one. All right. So cosine of 255 degrees. So we need to find two nice angles, either quadrantal angles or our nice reference triangle angles, right? Our 30, 60, or 45 degree angles that we can either add or subtract to get 255. 255, the angles that I can think of that are closest to that would be like 225, 270, right? If you're not sure, you could look back at our unit circle, right? We're looking for 255, which is somewhere in here. So we have a nice one at 240. But to get to 255, we'd have to add 15. 15 is not a pretty one, right? So if we look at 225, to go from 225 to 255, that's a difference of 30 degrees. So we could use that. We could use 225 degrees plus another 30 degrees gives us 255 degrees. And both 225 and 30 are nice, pretty reference triangle angles, right? So let's go ahead and rewrite this as cosine of 225 degrees plus 30 degrees. Okay, so this is going to be my first angle, and this is going to be my second angle. So I'm going to just scroll back up so I have my formula here. So we're going to use the sum identity for cosine. And our first angle is going to be 225, and our second is going to be 30. So using this formula, we know that this is going to equal cosine of our first angle, which is 225 degrees, times cosine of my second angle, which is 30 degrees, minus the sine of my first angle, which is 225 degrees, times the sine of my second angle, which is 30 degrees. right? So now that I have my values plugged into this formula, I don't really need to be able to see this formula anymore. Oh, you know what? I think I can get rid of this. How do I get rid of that? Is that what this is? No, that's autofocus. Oh, there we go. Ha ha. Ha ha. Success. All right. So now we've plugged in our values. So now we just need to simplify it, right? I need to know what cosine of 225 is, cosine of 30, sine of 225, and sine of 30. So let me just move this over to the side. Maybe I can get my unit circle in here. All right. So here's my 225. I want to know the cosine value. That's my first coordinate, which is negative square root of 2 over 2. So negative square root of 2 over 2. And then I need cosine of 30. So I go to 30 degrees, and I'm looking for the cosine value, which is the first coordinate. So that's square root of 3 over 2. And then I'm looking for the sine value of 225. So I go to 225 and I look for the second coordinate, which is negative square root of 2 over 2. And then I'm looking for the sine value of 30. So I go to 30, look at the second coordinate to get my sine value, which is 1/2. Okay. So now that I have my values filled in, now I can go ahead and finish out simplifying this, right? So a negative times a positive is going to give me a negative square root of 6 over 4. And here I'm going to get, I have two negatives here, so that's going to make this a positive term, right? Because negative times negative is positive, times another positive is still positive. And I'll get square root of 2 over 4. And then we want to make sure that we write it as one fraction. So negative square root of 6 plus square root of 2 all over 4 is our exact answer for the cosine of 17 pi over 12, right? Or cosine of 255. All right, so both of these examples, both number 1 and number 2 that we did here, we're showing how to take cosine of an angle and expand it using one of those formulas so that we could get an exact answer. Sometimes it's easier for us to take one of these formulas in its expanded form and condense it down in order to simplify. Meaning, sometimes instead of them giving you cosine of an angle value and you calculating the right-hand side, sometimes they'll give you the expanded right-hand side and you have to figure out what the left-hand side was. Okay, so that's what this number 3 is looking at. So the first thing I need to determine is, have I been given the formula for a difference cosine identity or a sum cosine identity? So if I look at my two terms, notice they're being added. So if I look back at my identities here, if I have two terms that are being added, that means I must have the difference cosine identity, right? So this addition right here tells me that I started with a cosine of something minus something identity, right? If I'm adding the two terms, then that meant I had a cosine identity where I had two angle values being subtracted. So I just have to figure out what are my angle values that are being subtracted. Well, I can see here, remember our identity says that we always do cosine of the first angle and cosine of the second. So just by looking at this first term, I should be able to tell what my first angle is and what my second angle is. So if I look here, I can see that my first angle was 173 degrees and my second angle was 83 degrees, right? So cosine of 173 minus cosine of 83 is the same thing as cosine of 90 degrees. And that's something that we should be able to find really easily looking at our unit circle, right? If I want to find the cosine value of 90 degrees, I go up here to 90 degrees, right? Cosine is my first coordinate, and I can see that my cosine value at 90 degrees is just 0. Right? So this was an example of how taking an expanded identity and working it back down to the left-hand side made it easier for us to find the cosine value than the other way around, right? Because the other way around, 173 and 83 are not nice values that we can look up on our unit circle, right? Okay, so where do we go from here? The other identities that we're going to start talking about is cofunction identities. So I don't know if y'all remember going over cofunction identities. We talked about them back when we were first introducing the idea of an acute angle. So remember, a cofunction identity was that if I have two identities that add up to 90 degrees, then I know that their sine and their cosine values are the same, right? Saying something like sine of 60 is the same as cosine of 30, right? Because 60 and 30 add up to 90. So we have cofunction identities, meaning the sine of one is equal to the cosine of the other one, or the cosine of one is equal to the sine of the other one. Okay, so we have these cofunction identities. So what we're going to do is we're going to use this identity that we're now familiar with, right? This is the one we started this section with, the difference identity for cosine. And we're going to derive, or in other words, we're going to prove this identity. Okay, so this is one of our new ones. Even though it's something we've used before, we didn't actually prove it. That if we have two angles, right? This angle is theta, this angle is 90 minus theta. So you agree that 90 minus theta and theta add up to 90, right? Because if I were to add, 90 degrees minus theta and a positive theta, the thetas would cancel out and it would equal 90, right? So if I have two angles that add to 90 degrees, then cosine of one of the angles is equal to sine of the other, okay? So this is what I want to prove, and I'm going to use this cosine identity to help me prove this, okay? So I'm going to start with this left-hand side. So if I start with the left-hand side says that we have cosine of 90 degrees minus any angle theta, right? That's 90 degrees or less. Well, if I take just this left-hand side, 90 degrees minus theta, this is a difference cosine identity, right? So that means 90 is like my first angle and theta is like my second angle. So I can plug 90 and theta into my cosine identity up here, which says to do cosine of the first angle times cosine of the second. So cosine of 90 degrees times cosine of theta degrees plus sine of my first angle, sine of my second. So sine of my first angle would be 90 degrees and sine of my second angle is theta. So I want to see how I can now go from this to this just equaling sine theta. So let's see if there's anything in here I can fill in. Well, two things, excuse me, two things that I see right away is cosine of 90 degrees and sine of 90 degrees. Those are values I can get off of my unit circle, right? If I look at 90 degrees here, cosine of 90 degrees is 0, right? So I can replace this with 0 times cosine theta plus sine of 90 degrees. If I go to 90 degrees and look for my sine value, it's 1, right? So sine of 90 degrees is just 1 times sine theta. So if I keep simplifying, 0 times cosine theta, that just cancels out, right? Because 0 times anything is 0. And here 1 times sine theta gives me sine theta, which is exactly what I was trying to prove, right? Is that cosine of 90 minus theta is equal to sine theta. So we have proved it, or derived it, or verified it. These are all words meaning we're trying to show that one side equals the other. Okay? All right. So that is one of our cofunction identities. Now we want to come up with the other cofunction identity, which is that sine of 90 degrees minus theta is equal to cosine. So it's really saying the same thing, right? We're saying if we have two angles that add up to 90, we can say that the cosine of one angle is equal to the sine of the other. So really all we're changing is the location of these two angles. We're calling this one theta, we're calling this one 90 minus theta, and this one we're putting the 90 minus theta as the sine and the theta in the cosine. Okay, so it shouldn't be too terribly difficult to prove, right? So we're going to take this identity that we just proved in part 1. We're going to use the cosine of 90 minus theta equals sine theta in order to derive this one. Okay, so this is what we're trying to prove. So I'm going to go ahead and start with, let's see. What do I want to start with here? I want to find sine of 90 minus theta. Okay, now we are using a generic example, so that's true for all cases, right? So 90 minus theta, where theta is any value between 0 and 90, right? I can pick anything I want for this theta. So I'm just going to write up here. Theta is an input. So I can replace it with any theta, right? So I'm going to pick a specific theta that helps me solve this. So I'm going to pick 90 minus theta to put in for this theta. Does that make sense? So I'm going to start with this identity that I know to be true. I know that cosine of 90 minus theta is equal to sine theta, right? This is what we just proved in number 1. Now this has to be true for all theta, right? All theta, any theta that adds up, any 90 minus theta and theta that add up to 90 degrees, this will always be true. So what I'm going to do is I am going to specifically change my input of theta to anything I want, right? As long as it's true on both sides, I could put anything I want in here. I could say 90 minus alpha is equal to sine alpha. I could say cosine of 90 degrees minus 100 is equal to sine of 100, right? I could put in anything I want as long as those two, as long as this statement remains true, which we know it's true. So for my input of theta, I'm going to specifically pick 90 minus theta. So what that looks like now is that cosine of 90 degrees minus 90 minus theta is going to be equal to sine of 90 minus theta. Okay, so all I'm doing is I'm picking a specific value of theta to put in for theta. Okay. Now what that allows me to do is I can now distribute this negative. So I have cosine of 90 degrees minus 90 degrees plus theta is equal to sine of 90 degrees minus theta, right? And notice what happens on the left-hand side is my 90 degrees combined to 0, right? So I'm just left with cosine theta is equal to sine of 90 degrees minus theta, which is exactly what I was trying to prove, right? That cosine of theta is equal to sine of 90 minus theta. So here we have proved it. Okay. Now this isn't something I would think that you could come up with off your head. I just want to show you how it's true and why it's true. Okay. I'm not going to ask you to derive one of these from the other. I think that these two I've shown for you, so I'm not going to ask you to verify those. However, Now that we know these first two to be true, we should be able to derive all these other ones. And this is something that I would expect you to be able to do, okay? I'm just going to say know and be able to derive, okay? So all of the ones that are in orange, so these two that I did, I'm not going to ask you to derive those because I did the hard work on that. But now that you know those two to be true, okay, so from this one that I proved and this one that I proved, you should be able to prove these four, okay? So I'm going to go through those for you really quick. Actually, I may only go through two of them, and then I'll let you derive the other ones, just so that you get a little experience with it, okay? So let's look at the first one. Let's look at tangent of 90 degrees minus theta. Tangent of 90 degrees minus theta, okay? So we want to prove that this is equal to cotangent theta. Well, the only things that we're given is that cosine of 90 degrees minus theta is equal to sine, and sine of 90 degrees minus theta is equal to cosine. So that's not telling us how we can plug things into here. So I want to think about, how is tangent related to sine and cosine? Well, it's one of those quotient identities, right? On our identities page, we know that tangent theta is equal to sine theta over cosine theta. So I'm just going to rewrite this as that ratio, okay? So this means that tangent of 90 degrees minus theta is the same thing as sine of 90 degrees minus theta over cosine of 90 degrees minus theta. And now we can use those two identities that I just proved at the top of the page to replace these, right? Because sine of 90 degrees minus theta, where's that at? Here. Sine of 90 degrees minus theta is the same thing as cosine, right? This is just cosine theta. And the same thing on the bottom. Cosine of 90 degrees minus theta, we know from the identity above, is just sine theta. So now we have rewritten this to be just cosine theta over sine theta, and cosine theta over sine theta is cotangent theta. So we have proven that one, okay? So the proof to prove cotangent is very similar, right? So I'm going to have y'all prove that one. I'm going to say practice. And then I want to show you secant, and then I'll have y'all try the cosecant one. Okay, so looking at secant, we want to show that secant of 90 degrees minus theta is equal to cosecant theta. Okay, so I'm going to go ahead and change this into something that I do know, because notice the only things that I have proven deal with sine and cosine. So I'm going to rewrite this as a cosine identity. So secant is the inverse of cosine. So I could rewrite this as 1 over cosine of 90 degrees minus theta, right? And then cosine of 90 degrees minus theta, that's one of the identities I just proved at the top of the page. Cosine of 90 degrees minus theta is equal to sine theta. So this means this is the same as 1 over sine theta. And then 1 over sine theta, that's a reciprocal identity, right? 1 over sine is the same thing as cosecant theta, which is exactly what I was trying to prove. Okay? So I did the tangent and the secant. I want y'all to try the cotangent and also cosecant. Okay, so somewhere on the page, wherever you have room left, go ahead and prove the second and the fourth identity. So go ahead and pause the video, and then whenever you are ready, or if you get stuck, unpause it, and we'll go over it. Okay? Okay, let's see how you did. So on the first one, we're trying to prove that cotangent of 90 degrees minus theta is equal to tangent theta. So we start with cotangent of 90 degrees minus theta, and we don't have an identity for that yet, right? So we're going to go ahead and write cotangent out as its quotient identity, which is that we can express cotangent in terms of cosine over sine. So I can rewrite this as cosine of 90 degrees minus theta over sine of 90 degrees minus theta. And now these two, numerator and denominator, I can replace using the two identities that were proven at the top of this page. Cosine of 90 degrees minus theta is just sine theta. Sine of 90 degrees minus theta is just cosine theta. And the ratio of sine theta over cosine theta does in fact equal tangent theta. So that's all we had to do to prove that second cofunction identity. Now we want to look at the fourth cofunction identity. So the fourth one is proving that cosecant of 90 degrees minus theta is equal to secant theta. So I'm going to start with cosecant. Now I don't have an identity to change this into something with cosecant, right? But I do know that cosecant is the reciprocal identity of sine. So I can first rewrite this in terms of sine, which I would write it as a reciprocal, 1 over sine of 90 degrees minus theta. And then sine of 90 degrees minus theta is one of our identities here, right? Sine 90 degrees minus theta is the same thing as just cosine theta. So 1 over cosine theta, that I can write in terms of secant because it's a reciprocal identity, okay? So this is something that I could potentially put on an exam, is to ask you to prove how to go from one to the other. So make sure you're familiar with one, those reciprocal identities, and also those quotient identities, but also being able to use our sine and our cosine, our cofunction identities to prove each of these four, okay? All right. So let's see how else we could use it. So these were just proving more identities. Here's how we're going to use these identities to actually solve for the theta value or the unknown angle measure. Okay, so let's look at this next page. I'm going to skip this first one because I'm going to let you do it. Okay, so I'm going to look at number 2. Now, this says that cosine of this angle theta is equal to sine of this angle 7 pi over 6. The only time that a cosine value is equal to a sine value is when we have cofunction identities, right? So if we have a cosine that's equal to a sine, this means we have cofunction identities. Okay, cofunction identities. So in order for two angles to be cofunction, they have to be complementary, right? In other words, they add up to 90 degrees. So that means theta and 7 pi over 6 add to 90 degrees, right? That's the only way that one's cosine value would be equal to the other one's sine value, is if those are cofunction identities, which means that our angles are complementary and they add up to 90. So we're trying to figure out what that theta value is. So the way that we're going to do that is using this idea that we know that they are complementary. So if we know they're complementary, we know that theta plus 7 pi over 6 has to equal 90 degrees. And then I want to go ahead and just solve for theta. Now, to solve for theta, I would have to move the 7 pi over 6 to the other side. And right now I have it equaling 90 degrees. Since this one is in radian measures, I'm going to go ahead and change 90 degrees to radian measures. So you can either multiply by that ratio, right, of pi over 180 degrees, or you can even look back at your unit circle. We're trying to convert 90 degrees. So if I look at 90 degrees, its radian measure is pi over 2, right? So I'm going to go ahead and just rewrite this as theta plus 7 pi over 6 is equal to pi over 2. Okay, and now I can move my 7 pi over 6 over. Now when I move my 7 pi over 6 over by subtracting they're going to have the same denominator, or I'm not going to be able to combine them, right? So my common denominator between 6 and 2 would have to be 6. So, excuse me. So I'm going to go ahead and just change this one so it has a denominator of 6 by multiplying on top and bottom by 3. So that way I have theta plus 7 pi over 6 is equal to 3 pi over 6. And now when I move this term over, I'll be easily able to combine them. So I'm going to subtract 7 pi over 6, subtract 7 pi over 6, which gives me theta is equal to negative 4 pi over 6. And I want to go ahead and reduce that because that one is reducible. So I have theta is equal to negative 2 pi over 3. Okay. Now, another way you could work this one, if you don't like dealing with radian measures, is you could first change this to degrees. So I'm going to say, could also solve by first converting to degrees. Okay, but I will warn you on my math lab, and if you did convert it to degrees, you would have gotten theta is equal to negative 120 degrees, okay, which would not be incorrect, but on my math lab, if they give you a problem with a radian measure, most likely they're going to want you to enter your answer with a radian measure, okay? So if you change it to degrees, make sure once you have your answer, you can use the unit circle, right, to go negative 120 degrees and end up back at negative 2 pi over 3, okay? All right, so what I want y'all to do is use the same idea that if it's a cofunction identity, we know that the two angles within that identity have to add to 90 degrees because they would be complementary, right, in order to have this cofunction identity. And I want y'all to try number 1, okay? So go ahead and pause the video, give that a try, and then when you're ready, play the video again and we'll go over it, okay? Okay, let's see how you did. So on this one, same idea. If you see a secant and a cosecant value equaling each other, and the angles are different, the only time that is true is if you're dealing with a cofunction identity, right? All those identities on that last page that we just proved, right? The only time you have a secant and a cosecant identity equal to each other is when the two angles are complementary, right? So when you see this cofunction identity, that means the angles must be complementary, which means they must add up to 90. So we're going to use that idea to be able to solve this. So our first angle theta plus our second angle 62 has to add up to 90 degrees. So I subtract my 62 degrees in order to solve for theta, which means that theta is equal to 28 degrees. Okay? All right, I want to show you 2 more, and then you'll be able to get started on your 5.3 homework. So at the bottom of the page, we can also use the sum and difference identities for cosine to rewrite other identities in their simplest form. So let's look at that. It says we want to use this addition identity for cosine, and we want to rewrite cosine of 90 degrees plus theta. So that's what we're starting with, cosine of 90 degrees plus theta. Notice we don't have any cofunction identities that deal with plus theta. All of ours were minus theta, right? So I want to use this. I'm going to consider this my first angle and this my second angle. So I'm going to use my cosine identity that says when we add 2 angles, we do cosine of the first times cosine of the second. So cosine of the first is 90 degrees. Cosine of the second is cosine theta minus, and then we do sine of the first and sine of the second. So sine of the first angle is 90 degrees. Cosine, oh, not blah, 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 blah. Sine of the second, which is theta degrees. Okay, so all we did was plug in our first and second angles into our formula right here, right? And now this is something we should be able to simplify by using our unit circle trig function values, right? So here I should be able to figure out what cosine of 90 is and what sine of 90 is. So if you need to, refer back to your unit circle. 90 degrees is right here, right, at our 90-degree angle, or pi over 2. And we can see that our cosine value there is 0, and our sine value is 1. So I'm going to put a 0 in for our cosine value and a 1 in for our sine value. So you can see that our first term is going to go away, right, because we have a 0 times something, and 0 times anything is 0. But our second term, we're left with -1 times sine theta, which is just negative sine theta. So this is the simplest form of writing cosine of 90 plus theta, which makes sense if you think about it, because this is very similar to a cofunction identity, right? And if we need the two angles to add to 90 degrees, our other angle would have to be a negative theta, right? And sine of a negative is the same thing as negative sine of theta. Sorry if that was too much. Anyways, I just want you to be able to plug it in and be able to write it in its simplest form. Okay? All right. Last example of this section is when they give you specific sine and cosine values of two given angles and their location, and then they want you to calculate either the sum identity for cosine or the difference identity for cosine. So let's look at one and how to simplify. So this says that cosine of this U angle is 15 over 17. The sine value of a V angle is -24 over 25. And it says U and V are in quadrant 4. And we want to find this. Okay. Now before I can find this, I need to make sure I fully understand these two. So the first thing they tell me is that both of these angles are in quadrant 4. Remember, quadrant 4 is down here, right? This is quadrant 4. So our U angle is somewhere down here in quadrant 4. This is U, right? And our V angle is down here somewhere in quadrant 4. Okay, so what I'm going to do is I'm going to use the values that were given to go ahead and complete these reference triangles. So I'm going to draw this as a reference triangle. I'm going to draw this as a reference triangle. Okay. Now on U, it says cosine is 15 over 17. So remember, cosine is adjacent over hypotenuse. So that means this adjacent side right here is going to be 15. And our hypotenuse is 17. So I need to figure out what the opposite side value is, right? Or our y value. So I'm going to use the Pythagorean theorem to figure out what that side is, okay? So I have x squared plus y squared equals my radius squared, right, or my c squared. So that means that 15 squared plus my own unknown y squared value is going to equal 17 squared. So I'm going to go ahead and move my 15 squared to the other side. So that means y squared is equal to 17 squared minus 15 squared. I'm going to go ahead and write out what those values are. 17 squared is 289. And 15 squared is 225. So when I subtract those, I get 64. Okay, now that's for y squared. Remember, we want only y. So I'm going to take the square root of both sides, which gives me y is equal to the square root of 64, which means that y is equal to 8. So this length is 8. Now, normally when we take the square root, in order to solve something, we have to do plus or minus. But here, notice, I'm solving for the y value. And I know that the y value is below the x-axis, so I can go ahead and determine right here that it's going to be a -8. Okay, you could do plus or minus here and then determine that it's in quadrant 4, so our y value is negative. Okay, however you want to go about that to determine the sign. All right, so now I know everything I need to know about my u angle. Now I want to do the same thing with my v angle. My v angle says that sine value of v is -24/25. Sine is opposite over hypotenuse. So that means this opposite side is -24 and my hypotenuse is 25. And what we need to know is this x value, right? So I'm going to set it up the same way. X squared plus my y value, which is 24 squared, is equal to my hypotenuse, which is 25 squared. Okay. So I'm going to go ahead and move I'm going to go ahead and write what these are. So I have x squared plus 24 squared is going to be 576. 25 squared is 625. And then I can go ahead and move that 576 to the other side by subtracting. So I end up with x squared is equal to 625 minus 5. Oh, I don't know why I'm writing it out sideways. That's silly. I can just subtract those numbers. 625 minus 576 is 49. And then I take the square root. So that means x is equal to plus or minus 7, right? If we're solving for x and we know the x squared value, we take the square root of both sides. So it's either going to be a +7 or a -7. We're in quadrant 4 and we're looking for the x. Notice the x value here is going to be a +7. Okay, so now I have all the values that I need to know about my angle V. So now that I know everything about u and v, now I can go ahead and solve for what I'm actually solving for, which says to find cosine of u minus v. So this is one of our cosine identities that we just came up with, right? Cosine, when it's a difference identity for cosine, that means we end up with an addition of terms. So I'm going to go ahead and just write out the formula. Hopefully we're super familiar with it, right? When we look for a difference, we're going to do cosine of the first angle, which is u, times cosine of the second angle, which is v. And then we're going to add, right, because we started with a subtraction, and our formula says that we do an addition, of our sine value for the first angle and our sine value for the second angle. All right, so now we have our formula. Now we just need to fill in these values. So cosine u times cosine v plus sine u times sine v. So cosine of u, that was actually given to us, right? Cosine u is 15/17. And now we need cosine v. Cosine v was not given, but we can figure it out because we have these values. So cosine is adjacent, which is the value we found, 7, over our hypotenuse, which for v is 25. Okay. Now I want to fill these in. Sine of u was not given, but I can calculate the sine by doing the opposite over the hypotenuse. So looking at our u angle, the opposite would be -8 over our hypotenuse, which was 17, right? And then sine v is the last value we need to find, and that one was actually given to us, -24/25. Okay, so we go ahead and multiply these together. So straight across, 15 times 7 gives me 105/425. Plus, when I multiply these together, a negative times a negative is going to give me a positive 192/425. And they both have the same denominator. So I can go ahead and add the numerators, which gives me a 297 over 425. And if you want to check, because we're looking for exact values, if you want to check on your calculator, you can type this in using your fraction button, and it will reduce it for you if reducing is possible. So your fraction button on some calculators looks like this one, A, B over C. Some of you have an X over Y button. Okay, so if I want to type this in, I would do 297. And instead of doing divided by to write the fraction, I'm going to use the fraction button over 425. And I'm just going to hit enter. And notice it gave me the exact same thing I just entered, which means that this fraction is not reducible. If I would have entered a fraction that was reducible, like let's say I put 4 over 8 and hit enter, it would automatically reduce that to 1/2 for me. So if you type this into your calculator using your fraction button and it doesn't reduce, then you know it's already fully reduced. Okay? All right. So that is the end of section 5.3, which is the sum and difference identities for cosine. You have 2 separate assignments for this section. You have your regular My Math Lab assignment, and you have a worksheet that only has 2 problems. But those 2 problems are verifying or deriving or proving, okay, that something is true. So I want to see you write out your logical proof of going from the left side equals the right side, or working both sides until they're the same, okay? So just like the 5.2 worksheet, this is actually a proof where you're showing your logical steps to show that one side is equal to the other, okay? If you have questions, let me know. Otherwise, I will see you on the next video.